Hello everyone. I'm uploading this recorded video as an alternative for my today's lecture, that is lecture on 20th January 2022. And because of some medical emergency, I could not able to take a live lectures today. But tomorrow again, the live lectures will be as per the schedule. So as you can see from this screen that from today I'll start discussing from the textbook. The name of the textbook is here, and the older version of PDF you can download from internet. I'm not sharing it. You can just search the name in Google, and you'll find the older version. And if you want to purchase a new version, then it's always welcomed. As I said at the beginning that when since I am following a textbook, so maybe I'll not share the PPT. I'll not prepare PPT every time, and you can see PPT I'll only share whenever it is required. Otherwise, I'll not share any PPT. I'll try to follow the book. Why I'm trying the book? I'm following the book. One important reason is I want to force you to read the book. Because no matter how I am teaching, at the end my lectures will be not enough to understand the concept of computer architecture. If you follow a book properly, it will help you lifelong. Why? Because after 1 year maybe you will completely forgot that what I have discussed. But if you study a textbook line by line, and if you underline some important points when you understand it first time, and then if you keep this copy with you, maybe in future also whenever you want to revise some basic concept of architecture, you can just read those particular section. Then it will be easy for you to understand. That's why I advise people to follow a particular book, especially for the core courses. Core courses means like the courses like computer architecture, OS, operating system, programming, like these we consider as core courses for BTech. Okay, so this is that's why I'm following the book. One more point here, since I am uploading it now, it is almost midnight, and tomorrow I will take another next class. So if some of you miss this particular lecture, then there won't be any problem to understand the lecture that I will take on Friday. So why? Because most of the concept that I will discuss today are actually I've already discussed, but I have to discuss it again here because of continuation of this book, because I have to start with chapter 1, right? So that's why I'm continuing starting from chapter 1. But the concept that I will discuss today are mostly I've discussed already in this course. So that's why when you read the book, it will be easy for you to understand. You'll also get interest on it. Okay, so it means that for tomorrow's lecture, that is Friday live lecture, that lecture is not directly depend on this lecture. So you can also watch this lecture on weekend, and you can stop it here also if you don't have time today, and maybe you can watch it on weekend. But you have to watch. There will be some points which have not discussed till now. Okay. Now, one more important point here. After few minutes here, you will see the when the actual content of this lecture will start. That actual content is not recorded now. That actual content is recorded almost 1 year back, and that content was recorded for a MTech course, not for you. But I have checked the video, and I think all the concepts are properly explained, and you can also watch it. Only thing that you need to ignore here is, I think that in one or two instances I mentioned that these most probably you have studied this on BTech. You may listen this type of line, but you can ignore that line, because instead of these two lines, this type of lines, I think I've explained everything from the basic, and a BTech student can also understand it properly. So please remember that from this point onwards, the video that I'm attaching here, it's a recorded video. But except this point, everything mentioned in that video is important for you, that which section you have to follow from chapter 1, and what are the things you need to study from chapter 1. Everything mentioned in that recorded video is important for you. Only thing that I am saying to skip is, if you listen somewhere that this concept you have already studied in BTech, so don't be confused at that moment, because this was a recorded video. Otherwise, everything is important. Also, in this recorded video, I have mentioned something about the previous two lectures. So here you have to understand whatever I explained in the previous two lecture in that course, that is same concept I've already explained you in the initial lecture. So every time when you listen this type of lines that regarding the previous two lectures, you have to understand that the content of that two lectures is already discussed in your course also till now. So let us start the recorded video. So there are in chapter 1, if you start reading from the beginning, there are many basic introduction about computer that I have already covered in the first two lectures. So I am skipping all those things. If you are interested, you can read the initial sections of these chapters, but those are not directly important in terms of exam. So that's why I'm starting from 1.6, that is called performance. Also from this point onwards, whatever I'll discuss in today's lecture, this is I think I have already discussed in my initial two lectures, but since I want to continue, or I want to relate this course with that this particular textbook. So I'm explaining all this concept that is written here from 1.6, that is performance. So what is performance? Why performance is important for a computer? So I think I've explained it in my previous class, that if you have two computer like C1 and C2, how can you say that which one is performing better, or whose performance is better? So one technique I have explained in last class, that we will run a particular program in both the computer and then find out the execution time. The computer which is executing faster will say that okay, performance of this computer is better. But sometimes the requirement may change, or you cannot every time you cannot measure the performance in terms of only in terms of execution time. Let us use a example. So if you read this book, you can see I am directly following the book. So if you go for defining performance, here means how to define that what is called performance. Okay, so if you see this table here, the figure 1.14, in this table it is there are different types of airplanes are mentioned, and they are different parameters. You can see passenger capacity, cruising speed, cruising range, cruising speed, and the passenger throughput. Passenger throughput means passenger per meter per hour. So this is the passenger throughput, means how many passengers you can deliver at a particular time. Okay, so if you see that if you from this table, from there are different airplanes, so how can you say that which airplane is has the better performance? So it means that by performance, what you are trying to measure means how you are defining the performance. If I am only concerned about the speed, then the last one, I think last one is better, right? If I only concerned about speed, then this one is better, because the speed is 544 faster than any other aeroplane here. But you can see the passenger capacity is only 146 here. So now if I want to send 400 passengers, if I want to send 400 passengers, then I don't think this plane is performing better according to my requirement, because my requirement is sending 400 passengers. So according to my requirement, I think we should go for this one. If I want to go for I want to send 400 passenger, then according to my requirement, the second one, Boeing 747, will perform better. So that's why the important point is how we are, what we want, and based on that we have to measure the performance. So if these two example that I've shown here, if I try to relate it with the computer, then it's like this, that if I have some small applications or standalone application that I want to execute in a computer, single one application at a time, then this first example is better. This type of computers is better, that yeah, which one is faster, because my job is just execute one task at a time. So better I will go I should go to the fastest computer, the computer which can execute much faster. But if I have multiple tasks, like I have multi millions of tasks or thousands of tasks that I have to execute simultaneously, in that case the important thing is not just execution time. The important thing is total task done in a particular time frame, right? So the first example is true for desktop computers or personal computer, where I most of the time we execute one application at a time. But consider a server machine. In server machine there are multiple applications, thousands of applications are executing, and for those server manufacturer or those who maintain server, for them it is not very important that how much time it is taking for one particular application. This is not very important because there are thousands of applications running simultaneously. For them the important thing is how many applications is possible to finish per unit time. That is very much important. So I think this is written here. If you go for here, there are two things. Response time. As an individual computer user, you are interested in reducing response time, means the execution time. Okay, but it's the data center manager often care about increasing the throughput or bandwidth. This is called throughput, means total task per unit time is called throughput. So as a data center user, as a server user, the main goal will be to reducing the throughput or improving the throughput or improving the response time. Improving the response time is important for individual computer user. So that's why here it is mentioned that how you will define the performance definition may be different when we go for different type of computers. But in this course mostly will follow the execution time or response time. Will not discuss about throughput, at least in the initial lectures. So now whenever you will read this book, always try to understand this point that is written in boxes. So what is called response time, it is written here. Response time is also called execution time. Execution time means total time required for a computer to complete the task. In this total time, all the time including disk handling time, input output time, operating system overhead and CPU execution time, everything is included. Okay, throughput also called bandwidth, another measure of performance. It is the number of tasks completed per unit time. So always try to remember these definitions, and don't just remember, you have to understand these terms. If any point is not clear, then please let me know. Okay, then if you go to this throughput and response time, here is an example given that suppose you have a computer and you want to do some changes in the computer. The first changes is saying that replacing the processor, that you want to replace you replace the processor with a higher speed processor, replacing the processor in a computer with faster version. That means change the frequency of the processor to a higher frequency. And then the second one is saying that there are two options, that okay, don't change the frequency but increase the number of cores. So that is option one, increase frequency, high frequency, okay, high speed. Okay, and second option is saying don't change the speed but increase the number of core. Instead of one processor, use two processor. So which one will improve throughput and which one will improve response time? So if we go for this one, high speed processor, if you increase the response time, obviously it will also increase some throughput, because it is increases, because assuming that there are multiple applications coming, A1, A2, A3, multiple applications are coming one by one to execute in the computer. So in that case, if we just increase the speed of the computer, then also it will it not just increase the execution time, it will also increase the throughput little bit. Okay, but compare this case, the same thing, A1, A2, A3, all these applications are coming to this processor where there are two cores. Okay, so in this case, do you think the speed is increasing, execution speed is increasing? No, because we have not increased the frequency of the processor. In first case we have increased the frequency of the processor. Here the frequency is same, but with same frequency we are using two cores. So in this case, for each individual application, we are not changing any execution time. So execution time remains same, but bandwidth is increasing. How bandwidth is increasing? Because in this case, when previously there was only one core, then in that case, only one application can be executed at a time. But here in this case, since there are two cores, two application can be executed at a time. So throughput is increasing in second case. Okay, but there may be a situation where the second case also increase the execution time. And what is that case? That case is very important. Assume that there are many instructions coming here. Instead of A1, A2, A3, assume that there are A1 to A1 to A1000. Many instructions are coming here. A1 to A1000. Many instructions coming, and these instructions are getting queued here, and they are getting queued here, and they are waiting for longer time before started execution. So in that case, if you have more number of cores, then you can reduce the queuing time, right? And if you reduce the queuing time, then obviously it is increasing the execution time also, because queuing time is also a part of execution time, because the application reached the processor but it cannot process, it is queuing it. So that queuing time will also include in your execution time. So if you have more cores, then and then the queuing time will reduce, and in that sense it may also increase the execution time. So all these points are written here, you have to understand it. Read this paper, this chapter, this section, you will understand it. And then there are some formulas written here of performance is 1 by execution time, performance x is greater than performance. So I am not explaining this because I think I have already explained it in my previous lecture. So read all these things, you will understand. Here it is written there how you can compare two computer. If there is a computer x and there is a computer y, and the performance is given of both the computer, how can you say that which computer is better than what? So for these the formulas mentioned here, you can use all these things I've already explained, so I am not explaining it here again. Okay, so I'll explain this example. This example is saying if computer A runs a program in 10 seconds, so computer A is running it in 10 seconds, okay, and computer B is running it in 15 seconds. This okay, so how much faster A than B? Obviously A is faster, right? Because A is completing the program in 10 seconds and B is completing the same program in 15 seconds. But the question is how fast A than B? Okay, so question is A takes 10 seconds, B takes the same program in 15 seconds. Obviously B is slower than A, but question is how much A is how much faster than B. So for this you can use this equation, performance A by performance B. Okay, so performance A by performance B equal to reverse, because performance A and execution time are inverse. Okay, so performance A by performance B means execution time of B by execution time of A, which is n. So execution time of B is 15, execution time of A is 10, which is 1.5. So A is 1.5 times faster than B, or you can say that B is 1.5 times slower than A. So sometimes it's very confusing that means whether we should go for faster term or slower term, right? So that's why the term that we use here is improved performance or improved execution time. So suppose here this is the execution time, right? Execution time of A, execution time of B is given. So which one is improved performance, which one is improving performance? Means execution time, lesser execution time is better or higher execution time is better? Lesser execution time is better, right? So in this case improved performance is coming from computer A, right? So if I go for another thing, right, uh, I think I have not explained CPI, so I will not explain start it here. But here important point that you have to remember is instead of mentioning it like faster and smaller, we will go for improve. Means 1.5 computer A is 1 point improving performance by 1.5 times as compared to B. This is a better term, improve. Okay, next I'll discuss that how to measure the performance. Till now I have mentioned here that execution time is the parameter based on which you can measure the performance of two computer. But I think in last class also I've explained that execution time is total execution time, including the queuing time, memory access time, input output time, all the time plus processing time, including everything is called the total execution time. So if I want to compare the performance of two processors, then including this using this called execution time is not very appropriate, right? Because when you go for input output, at that time the processor may not be doing any task. It may be idle in some cases. So using the total execution time to measure the performance of a CPU is not very appropriate. That's why we use another term, this is called CPU time or CPU execution time. You can see here it is written CPU time or CPU execution time. This is the actual time that is actual time when the CPU was executing the program. It was not ideal for waiting for the input output and all. So that is important. Okay, so I think in last class I've also explained the term called CPU time and the formula that how to calculate the CPU time. I'll repeat it again today, but I'll not explain it in more detail. But again, please remember to try to understand these definitions here. CPU execution time is written also called CPU time, the actual time the CPU spent computing for a specific task. User CPU time, system CPU time, you read it by yourself. I will not explain. This is very easy. Okay, so from now onwards we'll use two terms. It's called system performance and CPU performance. System performance means whenever we'll say the performance of entire computer, then we'll call system performance. In that case we'll use the execution time, because as a normal user, if I have two computers, or you can say two laptops placed in front of me, and I say which one is giving more performance, in that case we will go for system performance. Because suppose everything processor, both the processor is same. Suppose Intel i7 processor is installed in both the laptop, but in one laptop there is a SSD and another laptop there is a hard disk. So which one will perform better? Most of the time the laptop having SSD will perform better, right? So that is called system performance. But if we discuss about the CPU performance, then both CPU are same, right? So in that case the CPU must perform and similarly. So that's why please remember these two terms, system performance and CPU performance. Every time whenever I discuss about the entire computer, means including all the peripherals, input output, everything, memory, everything, then will go for system performance. And if we only want to compare the performance of two CPUs, then we'll go for the term called CPU performance. System performance means total execution time, CPU performance means only the CPU time. I hope you understand it. And then again, from this here you try to understand what is called clock cycle, clock period. I think these are very very simple thing, and you already know it from your BTech level, but read it again. Now we'll go for CPU performance and its factors. So CPU performance, I have already explained you now that what I am trying to represent as CPU performance. CPU performance means CPU execution time, right? So how you can calculate CPU execution time? CPU execution time means clock cycle for a program into clock cycle time. I think this formula I have already discussed in last class. CPU execution time means total clock cycle required for a program in a CPU. Suppose this is your CPU, okay, and this is the program A1 you want to run in this CPU. And this A1, when you are executing this program in CPU, the total cycles required here is 200. 200 cycles required in CPU to execute A1. So what is the time? Cycles into time required for each cycle. Sorry, the same thing is written here. Clock cycles for a particular program, which is suppose 200, and clock cycle time, time required for each clock cycle. If you multiply these two, then you will get CPU execution time. The same thing, clock cycle time and clock rate are the reverse thing, right? So the same formula you can also write like this. This is the same thing. You can easily understand it. Okay, so now you can see there is a example given. Let me discuss the example. The example is saying our favorite programs. We have a program which is running in 10 seconds in computer A with 2 gigahertz of clock. So you have a computer called A which is running a program in 10 seconds, and the frequency is 2 gigahertz. Okay, now you want to design a computer called B which should run the same program in 6 seconds. Okay, so what you see that as a manufacturer of computer B, your requirement that okay, I have to I have to run the same program in 6 seconds. So I have to do all the required hardware change such that the same program that is running in A in 10 seconds should complete here in 6 seconds. But for this you find out that okay, if to do this I have to increase the frequency, right? It currently it is running in 2 gigahertz, but if we want to run it in 6 seconds, I have to increase the frequency. But you have find out that if you try to increase the frequency, then somehow the number of instruction of this processor of this program is increasing. The program is here, suppose the program is A1. Okay, so if you somehow increase the frequency, then the other hardware details that is required to change, those hardware details will increase the or increase the clock cycle time is 1.2. Okay, what it is written here is that computer B requires 1.2 times more clock cycle as compared to 10, because this 1.2 times extra clock cycle is required because of the additional hardware required to increase the frequency. Now the question is, how much extra frequency is required? Means instead of 2 gigahertz in B, which gigahertz is required so that the program can run in 6 seconds? So for this, first what we will do, we will try to find out the CPU clock cycle required in A. So CPU time here is CPU clock cycle of A plus clock rate of A. Okay, then CPU time required is 10 second, it is mentioned here, so I have written, it is written here 10 cycle here, and the frequency clock rate is frequency is written here 2 gigahertz. From this formula, if you find out the clock cycle time, CPU clock cycle for A is this. Okay, so CPU clock cycle required for A is this. Now if you go for this formula, CPU time and this, then for CPU time required, need to be required is 6 second, so 6 seconds. And now here the CPU cycles required is 1.2 times of the CPU cycle required in clock cycle 1, so 1.2 into CPU cycles and then clock rate. Now we also know the CPU cycles of A from here, so we'll put it here, and then clock rate of B you can calculate as 4 gigahertz. So the thing here is, if you want to design a computer B where the same task A1 that was running in A in 10 seconds, and if I want to execute it in 6 seconds in B, then I have to set the frequency of computer B to 4 gigahertz. So this is the example here. Try to understand these small problems, because I may give some this type of problems in your exam, in like class test or mid sem. Okay, now coming to instruction performance, I think this point is also explained in last class, that instructions, what is the instructions, the main concept of instruction set architecture I have explained to you. So if I start from a hello world program, suppose the hello world.c, this is a C program. If you compile this program, then after compiling this, there will be a corresponding assembly language program, right? So I am writing this as hello world underscore ISA, instruction set architecture. There is a assembly language equivalent of this, and if you see the assembly language code, it's a sequence of instruction, right? I have explained it in first class. It's a sequence of instruction. So every program that you have written, after compiling it, there will be a sequence of instruction, there will be a total number of instructions. So when you execute the program in a computer, there should be a finite number of instruction executed every time. It's not like that the total number of instruction available in your computer will execute every time. It's not possible, because if you remember my first lecture where I was explaining program counter, I've explained there was a condition of if condition was there, right? So if this is true, then I'll execute this part. If this is false, then I may jump to that part. It's very simple, right? If true, I'll execute this part, else I'll execute this part. But there may be 10 instruction here, there may be 10 instruction here, so total instruction is suppose 20 plus instructions are there in this computer. But whenever you will execute the program, either you will execute this part or this part, so you may not execute all the 20 instructions. So that's why we use a term called instruction count. Instruction count is not that the total instruction available in computer. Don't miss don't think in this way, that instruction count means total instruction available in computer. Instruction count means every time when you run the program, total instruction executed at that time. If you run the program with some particular parameter, it may be executing here, and it may execute 10 instruction. Assume 10 and 20 to make difference. It may be possible, right? If condition here, there are 10 instruction, else part there are 20 instruction. So if you run this program with a particular parameter where it is going to this part, true part of this if, then it will the instruction will be 10 plus something, right? But if you are going for else part, then instruction will be 20 plus something. So instruction count means total instruction executed when you are running the program. So now if we go for clock cycle time again, if we previously what we said, that clock cycle time is total cycle required, right, plus CPU clock. Then total cycle required can be executed like this: instruction for a program, okay, total instruction of a program, and the CPI cycle, average cycle per instruction. This is called CPU clock cycle. CPU clock cycle means whenever we are running a program, how much cycle it is taking, how much CPU cycle it is taking. How to calculate it? First of all, we'll calculate how many instruction it is executing. This is called instruction count. Instructions for a program, we normally call it instruction count, IC. Okay, so I know a total instruction count, and then what extra I need the time or cycle required for each instruction. That is called CPI, cycle per instruction. It is called average clock cycle per instruction. So instruction count into CPI means the CPU clock cycle. Once you know the CPU clock cycle, multiply it with the clock cycle time, then you will get the CPU execution time or CPU time, right? I think these thing will be written next. So read here what is called CPU. Try to understand it is what is called CPI. It's important. I have already explained what is called CPI. I'm not explaining it more detail. See, there is an example here. You have to understand the example. I'm skipping it because it is easy. It will be easy for you to understand. If you are not understanding it, let me know. I'll explain. Now coming to this classic CPU performance equation. CPU time. How to calculate CPU time? Instruction count. See, instruction count into CPI. Instruction count into C. If we go only for these two parameter, what this is giving? These two parameter is giving us total CPU cycle required to execute a program, right? And for CPU time, if we know the total cycle, what extra thing required? Time required for each cycle, which is coming from clock cycle time. So multiplying these three parameters, you can get CPU time. Or instead of clock cycle time, if you want to go for clock rate, then instruction count into CPI by clock rate. So I hope you understood all this term: instruction count, CPI, and clock cycle time or clock rate. These three parameters, all these three parameters are very important to measure the performance of a particular computer. If you have, or CPU, not computer, CPU. So if you have two CPU and if you want to measure the performance, these three parameters are important. You just cannot ignore one parameter. It may be possible that the two processors, one is from AMD, okay, and one is from Intel. Okay, suppose their frequency is same, 2 gigahertz, 2 gigahertz frequency. Now you are running a program here called A1, the same program you are running called A1. Okay, same program you are running. So can you say that these two processors all give you the same performance or same CPU time? You cannot say. Why? I'm also assuming that the internal implementation are also same. Means how to implement internal implementation means in when you are executing a particular instruction, they are taking same amount of cycles and all. So if that is also true, then also since the clock rate is same, you cannot say that both will perform similar. One point here is the ISA may be different. If the ISA here is ISA 1 and here a different set of ISAs, maybe here assume that I'm using RISC-V, or maybe here I am using x86 or a different ISA, then when you will compile this program, then when you will compile here, the assembly code that will generated based on ISA 1, and here the assembly code that will be generated based on the ISA 2, right? So the number of instruction here in AMD and the number of instruction here in Intel may not be same. So that's why instruction count is also important. In similar way, cycle per instruction is also important. Cycle per instruction is important because if we assume, even if the frequencies are same, if the number of instructions are also same, it may be possible that internally how AMD and how Intel are implementing each instruction. For example, there is a load instruction, or there is a store instruction, or there is a add instruction. Exactly when the instruction is fetched, how each processor is implementing this instruction in micro level may be different, and these difference may need different amount of cycles. Okay, that's why the cycle required per instruction is depend on how each processor is implementing those instructions. So that's why CPI is also important, instruction count is also important, and clock rate is also important to measure the performance of a CPU or to calculate the CPU time. I think all these things that I have explained here is also written here in these sections. Please read this entire section and try to understand this concept, what is called instruction count. I have already explained. Okay, now let us go for this interesting thing. For this, let me zoom out this so that both pictures should be available. Yeah, both pictures are available here. So what they are trying to explain here is that there are two compilers. Now there is a compiler which need to take two decisions. Means there is a program, suppose A1. Now compiler wants to compile this program and to create the assembly language. But compiler has two possible option. Two possible option means these are the instruction set, instruction class available A, B, C to compiler. Okay, and compiler knows that this class instruction take one CPI is 1. Here for this type of instruction CPI is 2, and for this type of instruction CPI is 3. Okay, now the compiler has two possible options for to compile this particular program. One possible option is it should go for this code sequence, first code sequence. In this first code sequence, two instructions are there from class A, one instruction from class B, and two instruction from class C. Okay, and now it has another option also. This is another option. If it goes for this particular option, then there are four instructions from class A, one instruction from class B, and one instruction from class C. So either the compiler can generate assembly with this combination, or it can generate assembly with this combination. There are two possible options. Which one compiler should take? This is a question, and I think this is a question of code optimization in compiler. If you know the concept of compiler, there is a phase called code optimization, right? So or the code generation phase. In both phase, maybe in either of these phase, this type of decision may come there. Okay, I have two possible sequence are there. Which code sequence should I take to convert this high level program A1 to assembly language? Now first let us count the number of instruction in both the sequence. If I go for this one, the total number of instruction is 2 plus 2 plus 1 5, right? 5 instruction need to be executed. If I go for this, then 4 plus 1 plus 1 6 instruction need to be executed. So in terms, if we go for only in terms of instruction count, then sequence 1 is better. The compiler will say, okay, first sequence is taking only 5 instruction, let us go with first sequence and generate the assembly language code. Fine, but there is another point which we are not discussing, and the point is CPI, means cycle per instruction. Which cycle is taking how many, which instruction is taking how many cycle when will execute in this particular computer. And this cycle CPI chart is given here. In this CPI chart, it is given that okay, the class A instructions are taking 1 cycle, class B instructions are taking 2 cycle, and class C instructions are taking 3 cycles. So now let us calculate the total cycle required in each sequence. First sequence will require 2 into 1 plus 1 into 2 plus 2 into 3. How many cycles will be required? 2 plus 2 plus 6. So 10 cycles is required here, right? 10 cycle is required. I'm writing it here. 10 cycle is required. Okay, and now if we go for here, 4 into 1, 1 into 2, 1 into 3. How many cycles are there? 4 plus 2, 6 plus 3, 9. So now what is the conclusion? Even in the code sequence 2, the number of instruction is more, that is 6, but the total execution time is, the total cycle required is less. So the CPU time of the second code sequence will be less. So compiler should go with the second option. That's why these main purpose of this example is all the parameters are important. CPI as well as instruction count, all these parameters are important, and if those things are available to a compiler, then it can generate a better or a optimal assembly language code. Again, I'll advise you to read to try to understand this example here. I have explained it here, the same thing they have explained here, so try to understand it from here. Okay, now the bigger picture they have mentioned here. Bigger picture means CPU execution time for a program. The unit of measurement is second for a program. Instruction count will executed for a program. Clock cycle, average number of clock cycle per instruction. Clock cycle time is second per clock cycle. So you have to remember all these things. Okay, and then after this, understanding the program performance, this table I'll explain quickly. What I'm expecting from your side, I'm repeating it again, that you should read everything from the book. This is your task. Don't just depend on my lecture. First you have to watch the lecture properly, and then you have to read the book. That's why I'm not sharing any PPT. Your task is to read the book. Okay, now when you will come to this particular table is very important, that when you are designing a program, there are many phases, right? First we design the algorithm, then we write it in a programming language, then compiler converts it, and then the instruction ISA assembly language program is executed in the program. So let us see which part has affect the which parameters. Algorithm affects the instruction count and CPI both. How? Because how instruction count? Because the way you are writing the algorithm, if you write two for loop, if you write one for loop, based on this the number of instruction may change, right? So that's why algorithm increase or decrease the number of instruction the way you write the algorithm. CPI count or cycle per instruction may also increase or decrease, because I think I have not explained yet this point in class, but very soon we'll explain that there are different types of arithmetic instruction possible. Maybe add and division. This type of instruction possible. But when you go for add instruction, if it is taking 4 cycles, suppose, and then sorry, and then in that case the division may take 16 cycle. It may be possible like this. It means that all the instructions are not taking same amount of time, right? So if somehow when you are writing the algorithm you are using more division instructions, then your CPI may also increase. And if you are trying to use less number of division and multiplication instruction, and you are using more means addition and subtraction instruction, then then your CPI may decrease. That's why when you are writing your algorithm, from that point only instruction count and CPI may vary. Now programming language, when you are converting your algorithm and you are writing it in a programming language, then also the which syntax you are using, based on that number of instruction may increase or decrease. CPI may also increase or decrease, means if you are using a high level program where there are a lot of functions call, lot of subroutine calls are there, then in that case maybe some instruction you need the program will add which need more cycles to execute. So CPI may also vary based on which instructions or which coding style you are using in high level programming. And in compiler, obviously compiler will increase instruction count and CPI. And the example, the previous example where we are giving two code sequence, and based on this which code sequence should be taken, example just we have taken, right? So if you go to that example again, you will realize that how compiler can vary instruction count and CPI. And when after compiler, when the instruction set architecture, there is assembly language instruction set architecture is there. Instruction architecture means how instruction will be executed. So instruction set architecture can vary all the three. Instruction count can also vary, clock rate can also vary there, and CPI can also vary there. So read this table to understand all the point that I have explained here. This is very very important for you. And after this I'll quickly explain power wall problem. Basically, the main important section that you have to study from this chapter is 1.6. 1.7, I'm not expecting that you should read it in detail. Very quickly, I'll explain the power wall problem from this graph. See, in this graph, you can see from 1982, there are two things showing. One is clock rate of a processor and the power generated by this processor. So you can see till 2000, I think 2004 or 2000 here, up to this point, you can see here that frequency of the processors are keep on increasing, right? Or you can say clock rate of a processor is keep on increasing, but with this your power is also increasing. But after reaching this point, it has been found that it is not possible to increase the frequency of a processor anymore, because if we keep on increasing the frequency, the power consumption will also increase, and the corresponding heat that will generate from the processor will also increase, and it may be very difficult to manage the cooling technology and all if we keep on increasing the frequency. That's why from 2004 you can see the frequency rate is almost straight, means the frequency of the processor has not increased much till 2004, and the power is decreasing. Power is also decreasing. Then the question is how computer are performing better if the frequency is not increasing from 2004, till today is 2020, if the frequency is not increasing, then how we are getting better performance? We are getting better performance because from this point the concept of multi-core processor came. Initially we only concentrate on a single core processor where we only try to increase the frequency so that we can execute a particular program as fast as possible. But when we find out this problem, this bottleneck, that okay, we cannot increase the frequency more because of power issue, then the concept of multi-core came and said, okay, instead of one high frequency core, let us use four core in a computer. Suppose if we use 4 core in a computer, then all these 4 core can execute 4 different application at a time, right? So throughput is increasing. So when the from this point to this point, in this point we are getting better throughput from the processor because we are increasing the number of cores. And since we are increasing the number of cores but not increasing the frequency, the power consumption is gradually again decreasing. So that is called power wall problem. And after explaining the power wall problem, the next section, that is 1.8, they've explained the existence of the proposal of multi-core processor. I think this is explained here. After this, if you go for see the switch from uniprocessor to multiprocessor, so main point or main point for which we switch from single core or unicore processor to multi-core processor, that I have already explained because of power wall issue. So I think this point is enough for now. I'll not discuss more about multi-core processor now. As we proceed in this course, I'll discuss more about multi-core processor, more about the memory structure of multi-core processor. Everything we'll discuss, but not at this moment. At this moment, if you only know this main point why we started using multi-core processor instead of single core processor, that is enough. So at the end of this today's lecture, what I'll advise you, that read 1.6 section 1.6 from a textbook very properly, and other sections you can read if you want, if you are interested to know the concept of computer in more detail. Okay, so that's it for today's lecture. I am stopping this lecture here. If you have any doubt, you can ask, send me email. Thank you for watching this video. Have a nice day.